Okay, so I would like to tell you about a new way to find black holes in binary systems, which I call dormant black holes. And this is a project that have many collaborators, including 3 people in our group in Tel Aviv, Simchon, Sar, and Roy, and 3 people from the Ogle team, and many others. So I'll just first explain why it is important, and then how we do that, what is our technique, and then I will show you the first result, what I call the dormant black hole 1. Okay, so the known black holes in stellar binaries are quite few. The sample here is a list of all the known ones in binaries. There are some with high mass, companion, optical companion. The sample is quite small. There are 19 systems known where you can measure the mass of the black hole. So here is one of them. This is the M33 X7, which we participated in the discovery, and this tells you how people discovered, how the community discovered black holes in binaries. So this is X-rays. This is X-ray plot. This is the data folded with the period, and you see that there is an eclipse here, eclipse in the X-rays. All of them were discovered by X-rays.
This is the most precise black hole measured.
Yeah. He's teasing me, but all the time. All right. Anyway, so the idea is the following. Here is a star, in that case, high mass star, and the star fills its Roche lobe, so there is mass being transferred onto the black hole, and there is an accretion disk around the black hole. You don't see the mass being transferred, and this is rotates with the period, the binary period. So when the black hole and the accretion disk is generating the X-rays near the black hole. When the disk is behind the star, then that's the eclipse that you see here. And after you discover that, you look for the optical companion. I repeat, it is all of them were discovered by X-rays. And then you identify the star, and then you do radial velocity. So from the radial velocity, you can estimate the mass of the black hole. Well, here's the parameters of them, and the usual paradigm is the following: the 2 stars were in a binary. One of them evolved, quite massive, got rid of its envelope. Formed by a supernovae or implosion, whatever, formed the black hole. And then the last stage is when the other one started to expand and fill its Roche lobe, and mass is being transferred onto the black hole, and that's how you generate the X-rays. Here is, for example, the known masses of the black hole, which is, it is amazing that, this is Cygnus X1, the first black hole discovered in the 70s, but we still have very small sample, and we don't know much, for example, about the masses of the black holes and their distribution. So I'm preaching for the last 2 years or so that there is a way to enlarge this sample, and you can learn a lot about that, about formation of black holes and so on. And for doing that, I would like to call your attention that before it's getting active from the X-ray point of view, those systems spend most of their time in a dormant phase, what I call a dormant phase, when there is no X-ray generation, when that star, the secondary or the optical star, is not filling its Roche lobes. There is no mass transfers. There is no way to generate X-rays. And just to convince you that this is most of the time after of course, after the black hole was formed. Here is one specific system, one X-ray black hole that Roy calculated or downloaded a calculation of evolutionary track of that companion. And this is here when it is filling its Roche lobe, but you can see that most of the time it's spent on its main sequence phase when the radius was small and it was dormant. Even more so for that specific star, this is data, optical data, in the infrared data spread over many years. And you can see that even that one, which is now in the active phase, most of its time it is spending on a quiescence phase, what it's called, when the X-rays are not generated. So the number of active black holes from the X-ray point of view is small relative to the actual number of black holes in binaries. I could argue, I wouldn't bother you about this, that for every active black hole, there are probably 100 or 1,000 dormant ones. And the challenge is to find them. Of course, because the way of discovering them, X-ray, they are not. No X-rays. But I want to call your attention again to M33 X7. So again, this one, but when we followed the intensity, the optical intensity of the star, in fact, that was done in Mitzpe Ramon by Avi Sporer, was part of it, we see that there is an optical modulation of the star. And this is in B and V and R, and part of it is from its experiments. And you see that there is a huge optical modulation, up to 10 or more %. And this is what we call, mainly it is the ellipsoidal variability. So what I suggest is to discover these dormant black holes by this optical modulation, that you don't need really the X-rays in order to identify that this is a star which has a massive companion. Here is, for example, Cygnus X1, the first one. It's a very bright star, magnitude 9. And this is the optical modulation, and you see it's very clear. Anyway, so the idea is to search for this modulation. For that, I will introduce you to BEER, which is a algorithm that Simchon and I developed for other purposes. And just very quickly, so the BEER algorithm is searching for stars that have, in binaries, that have beaming, ellipsoidal, and reflection effect. This is why we call it the BEER. And just very quickly, the main one of the three is the beaming. The beaming effect is causing a source of light that is moving towards you to increase the brightness that you measure. It's not only Doppler effect, it's something has to do with the beaming of the light. And if you have a binary and you are here observing it, just this is the source of light, then because of the motion, you will get enhancement of the brightness when the star is moving towards you, and the decrease in the brightness when the source is moving away from you. Here is the ellipsoidal. The ellipsoidal is caused by the tidal force that is acting on the star, which deforms the shape of the star. So sometimes you see that longer part of the star and you get more light, but when the binary rotates and you see this side, which is the small size of the star, you get a decrease in the brightness. And of course, there is reflection also if it happened that this one is also a source of light. Anyway, so just to put these three effects in perspective, let's say that you have a binary with eclipse. It's two eclipses, and let's say these are the primary eclipse, this is the secondary eclipse. So the beaming effect will look like this. the reflection would be like this. And what is most important in our context is the ellipsoidal. Ellipsoidal has the frequency of half the period, half the orbital period. You get 2 maxima and 2 minima during the binary period, and when you put them all together, this is how it looks, and when you add them up, this is what you see. So if the 3 effects are in action, you see 2 maxima. This is because of the ellipsoidal. You see that this maxima is higher than this one. That's because of the beaming. And you see that this minima is brighter than this minima. This is because of the reflection. Anyway, so this is a very distinct signature of a light curve of a star that indicates that there is a companion. And here are the equations. So this is not, although you could think that this is a small effect, but in fact it was observed. It was observed many times by us as well. These are real light curves that you can see exactly the same things. And we applied that to the Kepler light curve, which wasn't that easy, but we found many of them. Here is, for example, 7, or here is six examples that we analyzed the light curve of Kepler, of the satellite, which is very accurate and spanned over 4 years. And we identified this signature, and then what we have to do, we have to go to a telescope and do radial velocities in order to confirm the existence of the companion and measure its mass. Okay, so I just remind you that this is the light curve of a real black hole. Another one, right? So now, in order to find a black hole, we have to analyze many light curves, because I can argue that 1 out of 10 million or of 1 million stars have a black hole companion. So you have to have a big data set, big light curves in order to find them. So luckily enough, there is, as Shri discussed, it's a big data phase of astronomy. So we have available many millions of light curves to analyze, including, of course, Ogle on the LMC and SMC, and the bulge that have 70 million, and the bulge has 400 million stars. You should analyze them and identify the good candidates, and then after identify them, you should go and observe them and confirm that you found the black hole. So it's not easy. You have to analyze something like 1 billion light curves and go through that, and the art is to identify the false alarm cases where something else mimics the signature that you are looking for. Anyway, here is, for example, the Ogle ellipsoidals that they identified in their data. And again, as Shri discussed, and Andre did that already, that they put the data in public. So when they identify ellipsoidals, they put them in public so we can go and analyze them. So this is the color magnitude diagram of those. And here is one of them that we analyzed from the bulge. This is our type of analysis. I won't go into the details, but this turned out not to be a good candidate. But this one here, hope you see that turned out to be a very good candidate, and in fact, not only a candidate, but a black hole that I call the Dormant Black Hole 1, DBH1. So here is the data. This is the data zoomed over 2 seasons from Ogle. Here is the whole data of Ogle of 15 years. And here is a simple power spectrum of the data. You see very clearly there is a huge peak here. So it's the peak it's in 50 days, but the orbit is, of course, 100 days because it's half, the ellipsoidal is half the period. And this is the Ogle data folded with 101.039 days. I'm not claiming that Danny wouldn't tease me. I'm not claiming. I'm saying I'm not claiming that this is the exact period. Yeah, right. Anyway, it turned out that this star was also observed by Macho. And Macho also put the data public, so we went and downloaded the Macho data, and it fits perfectly the same period with 3 harmonics. You see here the model, which is not a physical model, but just fitting 3 harmonics. Very, very, very clear.
So it's just, it's basically only ellipsoidal here, right? There's no beaming or reflection.
Well, you could argue that this one is a little bit higher than that, but it's not significant, and it's basically mostly ellipsoidal, yes. In fact, we also went to the Harvard plates, not the plates themselves, but they digitized some of the photometry, and it's also on the web. And it turned out that this one was observed for 60 years. 60 years, you don't see much, but if you fold the data and bin it, you do see. Even there, you see something. It's not exactly the same, and we have to still work on this. But this also shows that this is the ellipsoidal, if it is ellipsoidal, what is going on for maybe close to 100 years. It turned out that there is radial velocity already, this observed, because you have, this is not enough. If you see ellipsoidal, it's not enough, but it turned out that somebody made radial velocities, and we fit the radial velocities with the period, and fits exactly the same, and from that you can see that from the amplitude of the radial velocity, it means that the minimum mass ratio is something between 2.5 and 5. And that means that the unseen companion is much more massive than this one, the one we see. And so we went, and took very, very good spectra of that. This is part of this. I know you cannot see that, but that's. You
can't see it either.
Yeah, it's 8,000. It's 8,000. And we took another 3 radial velocity measurements. This is very recent. And again, it fits very well, and from that we can estimate the mass of the 2 stars. So I'll try to explain that. Because this star is in the LMC, we know the exact distance to the star. From the very good spectra, we know the temperature very well. So from that, we can derive the radius of the star. So it's a giant, it's 52 plus minus 2 solar radii. So we know that the Roche lobe of the unseen companion must be at least, the Roche lobe of the star has to be at least 52 solar radii. So this is M1, this is in the plane of M1 and M2, so that it means that the system must be on the right of this curve. On top of that, we have the radial velocity and the amplitude of the ellipsoidal. From all that, it has to be sin I must be less than 1, so it cannot be larger than this. So the solution is really around that part of the parameter space of M1 and M2. So this is M1 and M2. So M2, which is the black hole, it's one of the best measurement in mass. It's 8 plus minus 1 solar masses. And one could argue maybe it is a main sequence star with 8 solar masses. Couldn't be. Even if we assume that the companion has only 4 solar masses and main sequence, this is the giant. This is the spectrum of the giant. a model for the giant of 52 solar radii, and this is a model for a B4 star, which has only 4 solar masses, and at the blue end, the ratio must be at least 3, and in fact, what we have is 8 solar masses, so it must go something like this. So the brightness of the 2 stars, if the other one would be a main sequence, would be comparable at that range in the blue. And we have very good spectra. We got spectra from SALT and from Magellan, from MAG-E, and from Mike. Here is one of them. This is the spectrum. This is the model of the giant. And when you just fit this to this, you get something which is very, very well fit. And if there would be a B star, only before we should see something like of that, and there is nothing here. So that rule out, it's redundant. I don't think this is really necessary after we really derived in a very narrow range the mass of the companion, so it's 8 solar masses. So I think all that shows that we discovered the first black hole around the giant with a period of 101.039 for days. What hold me, was that we took one spectrum. This was done in South Africa in March, and we saw this huge emission line in age alpha. And when we got better spectra, we saw this is age alpha, and this is even in age beta, you see some emission. And that was kind of a surprise for us. But it turned out that all the black hole binaries, even in quiescence, show age alpha emission. And the model is that some of the matter is transferred a little bit, and that generates a thin ring or a thin disk on the edge of the Roche lobe of the black hole, and that's what generates this age alpha double peak emission, and that's exactly what we see. So even the peaks, the separation between the peaks fits with the velocity you expect from a test particle rotating around the black hole at the edge of its Roche lobe. So everything fits. So I think this is we can conclude that this is the first black hole. So here is, just to put in context, this is a log period of the known systems, and this is the mass of the black hole. So this is the new discovery or detection or whatever you call it. And you can see that all the known ones were with a quite short period. The median here is half a day. Half a day. Yeah, somewhere. This is 1 day. So half a day. Yeah. So this is way out. So apparently we have a big population of black holes with binaries that we were not aware of.
What's the 30-day one? That's still an accreting one?
Yeah, I don't remember its name. Yeah, all those were discovered by X-rays, all of them. Okay, in fact, we have another candidate. This is another candidate, again from Ogle, but we are working on that one. We also have radial velocity. We can derive the masses. We didn't do that in the very accurate way that we did for the one, and we got a few more measurements for that. Fits with that period, and again, there is emission, but there is apparently a 3-component emission here. So the conclusion is that there is a population of dormant stellar black holes. They are begging us to discover them. They are waiting impatient. They sit in dark like a good Jewish mother. They sit alone in dark, and they are waiting for us to be discovered, and some of them are in wide binaries, and this is apparently what we know is just the peak of the iceberg, the tip of the iceberg. Thank you. Ready? Yes.
I'm not disagreeing with this method, but it's very biased.
Absolutely.
No. I mean, the only way you're finding this is that you've got to raise tidal forces. So the other star, the secondary, has to be, for most cases, filling its Roche law.
No.
Well,
it does not
it
need.
Doesn't have to be. It doesn't have
it
to
can,
be.
It can be, the filling factor can be 0.9.
Yeah, but look at the equation. It goes as cube of that radius.
Correct.
That star, okay? So I'm saying, so it favors
Correct.
the star, the situation where Roche law transfer is about to start, it could be a bit below.
Yes.
Right? And the very fact, in your DBH1 and DBH2, the very fact you see a alpha in emission tells you,
That's
in
correct.
fact, it has already undergone mass transfer.
A little bit, yes.
Okay?
I agree
And
completely.
So these are dormant, actually they're dormant accreting systems, and because the orbital period is long, the dormancy is actually also correspondingly long, just like in recurrent novae. So
Absolutely correct.
I'm not saying it's, so you will find slightly earlier versions of like AO 620 and so on.
Correct.
And there will be longer period because that's exactly. So I would say the next exciting thing, it's great. I mean, the more you find with these things, is really to find the very large population of black holes which are in that period very short where for the several billion years nothing is happening. Okay, so every time we find one of these, the delta t of this duration divided by the delta t of evolution, I don't know what that factor is, 1,000, 10,000 maybe. So this is where I think dynamic spectroscopy will really be the way to go.
A, I agree completely. B, there is another way, and this is with astrometry. And that's Gaia. Gaia is astrometry, and there was a paper about this, as you probably know. And also about radial velocity, because Gaia will have radial velocity of all stars brighter than 12. Very crude radial velocity, but for that is enough. No, I agree. With all you said, I agree completely. Yes, and I'm thinking of that a lot. Yes, definitely.
Kind of a devil's advocate for your
Please.
argument that it is not a star as a companion. What if we have a triple system and there are two close, two solar mass stars? It will be an order of magnitude less than your curve.
Okay, so first of all, we concluded that the mass is 8. So
it's simple. You see the double horn H alpha, and you in fact see one is slightly blue and higher intensity. This is a dormant ring that is active, and we know already the dynamics of the system. I don't have the imagination for triple star, but
I do.
the simplest interpretation is this is in dormancy.
No, of course. But because we concluded that this is 8 solar masses, the unseen companion, even if you want to divide them exactly into 4 and 4, I showed you already that 1, 4 should be seen.
Yeah, but why did you put the curve of 4? Because there is uncertainty for this number of 8, isn't it?
Yeah, of 1, very, very, very small uncertainty. And besides, the period here is 100 days, so you need a short period in order to be stable. Otherwise, it's
Very close binary and wide.
Yeah, I don't think this will work.
Yeah, there's a simple last test you could do. Go and look for lithium. Do a high resolution thing. If you see it, you're done. All this black hole system show lithium in absorption. It's been a strange, there are theories, but I'm giving you a fact.
Okay, well, we should go into and check. Say it again? I have the data. I don't know if it's the signal to noise is large enough. But we can try.
So your algorithm highlighted many ellipsoidal events.
Sorry, I stopped.
Your algorithm highlighted like dozens of ellipsoidal events, and you said that many of them are not dormant black holes. And you said you won't go into details, but what are the other scenarios that would give you an ellipsoidal light curve, which you concluded and why it's not what you want?
Yeah, the main, I think that the main thing, the main false alarm is that it has a mass, it has a companion, but not black hole.
So it makes it a star, but
Yeah.
been seen, or
Yeah, well, in fact, we had a few cycles that we identified 10 candidates and went to the telescope and observed them, and all of them failed. And in one cycle, all of them were double line. But since then, we learned how, I think, to do it better. But now that we show that we can do it, so then the game is different, I think.
The religiosity that you had, was it a coincidence that it was before?
Yeah.
And the fact that nobody before you analyzed it was just chance?
No, that's, people overlook that. What can you do? Too bad. For them, or too good for us.
Yes.
Well, in fact, we invited them to join. So one of the in the list